Hi everyone, I'm Yiming Bian from Beijing University of Posts and Telecommunications. It's my pleasure to present our recent work about high-rate point-to-multipoint QKD network on QCrypt. Our collaborators are from BUPT, the Institute of Southwestern Communication, and Peking University. I'm so sorry that I cannot make an in-person talk because I haven't achieved my US visa yet. But I will attend the conference online for the Q&A. Otherwise, you can contact me through my email. Okay, now let's first review the point-to-point QKD system. The point-to-point discrete variable QKD system can achieve the transmission distance over 1,000 km and chip-based system. And the continuous variable QKD system can achieve over 200 km transmission distance and the chip-based Gaussian modulated coherent state system. These achievements support the long-distance interconnection and scalable deployments, which speed up the development of QKD network. Now the QKD network can support the connection of the nodes within a city, between different cities, and even the satellite-to-ground network. As we can see, the fiber optic QKD network is the mainstream method to access massive users, which consists of the backbone network, the metropolitan network, and the access network. Here is the network topology. The topology of the backbone network is point-to-point, while a metropolitan and access network include many point-to-multipoint connections, which is more complicated. The network nodes within the metropolitan distance can be connected with the mesh, star, and tree network. These complex connections raise the requirement of the networking efficiency. In 2013, the proposal of the quantum access network provides an efficient networking strategy. It uses the passive optical network to connect the node and the end users with a simple topology. Moreover, the network node is reused, therefore the network resources is saved, which is suitable for large-scale deployment. However, it also has some bottlenecks. To access more users, more channel loss is introduced, leading to the reduction of the network performance. Since the network node is reused, the multiplexing is necessary. The mostly used time division multiplexing causes the reduction of the repetition frequency when more users access. Therefore, the network is limited by the number of users. The mainstream existing countermeasures, including the using of optical switches and FDI or WDI. The optical switch solution can control the loss caused by the beam splitter, but it still suffers the reduction of the repetition frequency when the users increase. The FDI or WDI can solve both issues by increasing the band. However, both of the existing solutions make the network complicated since they require hardware adjustments. Therefore, it is natural to consider whether the above two issues can be solved by an improvement on protocol layer. Our solution is to use the continuous variable system. Here, a CVQKD transmitter is deployed as the sender, and a CVQKD receiver is owned by each end user. Different from the single photon protocols, the preparation of a single coherent state makes all users response. Therefore, we can perform a multi-user security analysis and parallel key distillation to enhance the network performance. The key point of the multi-user security analysis is a tight parameter estimation with all end users' data. With the entanglement-based scheme, we can estimate the whole system based on the modulation and detection data. The whole-level bound can be calculated with the covariance matrix representing the system before and after detection. When more users access in the network, though the channel loss is enhanced, more data is provided for tighter security analysis. This can help to overcome the influence of the channel loss on system performance. The parallel key distillation means that all bulbs distill secret keys with the same modulation data. Therefore, the correlation between different bulbs' raw data, which is the classical mutual information, should be removed. Different from a two-user case, the privacy amplification should ensure both security and independency. Here we show two strategies for removing bulbs correlations. The first one is a pessimistic bound, where we remove the sum of bulbs correlation and Eve's knowledge, while the second one is a tight bound, where we only remove the largest one among bulbs correlation and Eve's knowledge. Specifically, the first case is that the other bulbs cooperate with Eve. When we define a privacy amplification function, this case means that the bulb's modes are combined with Eve's modes, therefore the leaked information is increased. Actually, bulbs and Eve are independent. Therefore, when we want to simultaneously ensure the independency and security of the secret key, the other bulb's modes and Eve's mode can be treated separately, like this. For privacy amplification, when the amount of the mutual information between bulbs is removed, the independency is ensured. When the mutual information between bulb and Eve is removed, the security is ensured. Therefore, we only need to remove the maximum part of the above two parts. Then, both the independency and security are ensured. This enhances the efficiency of the privacy amplification. Now let's analyze a practical issue on the unperfect error correction. Normally, we publicly transmit the syndromes produced by bulb for error correction in a reverse reconciliation case. And the leakage of the secret information is considered as its length. However, since the raw data of bulbs are correlated, the syndromes prepared by bulbs are correlated too. Therefore, the syndrome produced by bulb 2 may also leak secret information of bulb 1, which leads to a cross-information leakage and weaken the performance. By encrypting the syndromes with one-time pi, the issue above is solved. The encrypted syndromes would not leak information anymore. Instead, it will consume the existing secret key bits with the same length. This is the same amount as the leaked information of a traditional method. From this figure, it can be seen that the secret key rate would not be reduced. We do need a secret key bit string for starting the protocol. However, as long as the protocol is started, the secret key rate no less than the traditional error correction strategy can be achieved. The key point is once the syndromes are encrypted, it will not leak information. Equivalently, it turns into the consumes of the existing secret key bits. The difference between secretly or publicly transmitted syndromes is whether the secret information is consumed in the current round or the last round, so the reconciliation efficiency is not affected. Another practical issue is that the receivers in the network node may not be trusted. Thanks to our security analysis based on covariance matrix, we can flexibly exclude the bulbs which may not be trusted by adjusting the size of the covariance matrix. Moreover, if we do not know which bulb can be trusted, but we know how many bulbs can be trusted, we can sift the worst bulbs for a worst-case security analysis to avoid the trusted party issue. The simulations on the mutual information shows that in a normal channel situation, Eve's knowledge is always higher than Bob's knowledge when Bob's correlations. Therefore, the removal of Bob's information is included in the process of removing Eve's knowledge, which proves that the correlation removal is high efficient. The secret key rate distance simulation shows that our security analysis can support a long transmission distance and a stable network secret key rate within 25 kilometers, which is suitable for building an excise or metropolitan network. This is our network structure. It is a continuous wave Gaussian modulated system with polarization multiplex, quantum, and pilot signal. Two AOMs are used as an optical switch for controlling the real-time SNU calibration. The phase noise caused by the two free-running lasers is compensated by DSP. The quantum signal and the reference signal are separately detected after demultiplexing. We developed a series of key technologies to support this network, including the multi-user security analysis, the parallel key distillation, the DSP, and the real-time SNU calibration. Here is the experimental results with a 1 to 16 beam splitter in the optical path. Though we only access 4 users, which means we only trust a quarter of the users in the network, the performance reduction caused by the channel loss is well compensated. An average secret key rate of 4 Mbps with 15 dB channel loss is achieved, which is hard to achieve with a CV QKD system based on a point-to-point security analysis. Here we show more experimental points. As we can see, the end user can achieve high key rate within a size distance. And the 1 to 4 network in 18 kilometers is even better than the existing network using WDI, where the channel loss and repetition frequency are both stable when the users increase. Finally, we came to a conclusion. We realized a multi-user QKD based on the passive optical network. The point-to-multipoint protocol, including the multi-user security analysis, which makes full use of the legitimate parties data for fighting the beam splitting loss, and the parallel key distillation, which raised the actual repetition rate without any multiplexing technologies. Our high-speed multi-user system is with simple structure and high capacity. In the future, we will make some progress on high-speed chip-based network for the scalability, and we will do field tests and co-propagation with classical signals. That's all. Thank you for your attention.
Thank you very much. Yiming, are you online?
Yeah, I can hear you, and I'm online.
Great,
can
perfect.
You hear me?
And we can also hear you.
Okay.
Questions in the audience.
Thank you very much, Yiming. Here, Tobias from DTU. I have a question to your experiment. You say that you have this, is it an AOM or so on the transmitter side for the real-time shot noise unit calibration? Can you explain this a little bit more? What you're doing?
Yeah, the two AOMs are acting like optical switches to control the on and off of the quantum signal, and we adopt the one-time shot noise unit calibration method. Therefore, we only need to switch the quantum signal. When the quantum signal is on, we are making the QKD precise, and when the quantum signal is off, we are doing the shot noise unit calibration. And since the AOM can switch very fast, therefore our calibration precise and our QKD precise is really near, and therefore the time gap is no more than 1 ms, 1 millisecond. Therefore, we think this is a real-time shot noise calibration precise.
If I'm not mistaken, this shutter was at the transmitter side. So if you measure shot noise when it's shut off, you still measure the excess noise through the channel and count that as excess noise, as shot noise.
Oh, you mean the excess noise from the channel is included? But
yes.
Okay. But when we switch off the quantum signal, we think there are no light injected from the channel. And if you look at the experimental structure, we also deployed some power meter to monitor the channel, the power from the channel. Therefore, when we are doing the one-time short noise unit calibration, we can monitor we also monitor the signal from the quantum channel, and we find there are no we can say there are no power from the quantum channel. Therefore, we think we are not suffering the excess noise.
Thank you.
So we could take one more question, but can I have the next speakers come down? Okay, other questions for our current speaker? I'm going to ask one question, Paul Kwiat here. What is the scaling as you go to more and more nodes in terms of the total amount of key that you're generating between any pair of nodes? Is it how does that scale with the total number of nodes that you have? Do we know that?
You mean the total number of the nodes in our experiment? There are the maximum node we can access is 16, but we only access 4 nodes in our experiment, and the security analysis is based on 1 transmitter and 4 receivers. Therefore, we can say one node, 1 transmitter as acting.
I guess I'm asking a more theoretical question. If you had n nodes and they are all transceivers that can transmit and receive, what is the scaling in terms of the rate? You could have a benefit because there's saturation effects. I'm just wondering if you have a sense how it scales with the total number of nodes.
Well, the scale of the total number of the nodes, I think, may be from 20 number to maybe 100, the scale of the nodes.
Okay, great. Thank you.